Hi, everyone. I'm Galit Katari-Vaslevi, and I'm the head of the biomaterial and 3D printing laboratory. We are part of the biomedical engineering department in Ben-Gurion University of the Negev. Oh, sorry. So our research focuses on developing advanced materials and treatments for patient-specific medicine. And we are using additive manufacturing technologies to do so. We are using different additive manufacturing technologies, actually all of them. So, sorry. I will give you short examples, and then my students will give you more details about it. But we are developing bone implants from metallic lattice structures and from high-performance polymers. We are using silicons to develop novel scar treatments. And we are using organic materials and also cells for bioprinting of bone and skin tissue. That will be in the future. And my students now, I have 4 graduate students that will present their project for more details. And the first one is an MSc student, Shlomi Digorker.
Thank you, Galit. Hello, everyone. My research is about the 3D printing of patient-specific metallic lattice bone reconstruction implants. This research is in collaboration with Triton Technologies. The samples I've tested with 3D printing using the Moject technology of Triton. Briefly, the layer-by-layer build process include mold forming, in which high-resolution print has jet and ultra-thin layer, creating a layer mold. Material deposition, in which a metal paste is applied into the molded cavities. Drying and hardening, in which the build rest goes into a thermal phase, hardening the new layer. And real-time visual inspection, in which a high-resolution camera analyzes the new layer, making sure it conforms to the final model. If it does not, the defective layer is removed, and the item repeats the previous layer without affecting the process. This process repeats layer after layer at an industrial speed. After finishing the build process, the finished build trays go into post-processing that include demolding, using mold removal solution that chemically dissolves the entire mold material, resulting with clean and robust grain parts, and sintering that make these parts fully functional. For a detailed explanation about the molded technology, you can visit the booth of Triton at hall number 12. The following results were obtained by the characterization of a 316L stainless steel alloy. The microstructural characterization included examination of both the XY and XZ planes of a printed cubic sample in order to examine whether there is dependency in the printing direction. Here we can see microscopic images of these planes that reveals the presence of a primary phase of an austenitic matrix and a secondary phase of ferrite. The presence of these phases is also indicated by an X-ray difflection analysis of both planes. As part of the corrosion behavior evaluation, I divided it into 3 areas and examined whether there is consistency between the different areas in terms of corrosion resistance. The tests were conducted in a solution that simulated the physiological environment, PBS. Here we can see the corrosion resistance in terms of potentiodynamic polarization and electrochemical impedance spectroscopy curves. The obtained curves in each plot demonstrate high corrosion resistance and that there are no significant differences between the examined areas. The in vitro evaluation included seeding of human bone cells on printed lattice samples and follow incubation for several time periods up to 28 days. At the end of the incubation periods, the bone formation was evaluated using fluorescent staining. Here we can see microscopic images of lattice samples that were incubated for 14 and 21 days. The blue DAPI staining, which represents the cell nuclei, indicates the cell's attachment to the surface of the samples. The red staining, which represents the calcium deposition, demonstrates how the seeded bone cells deposit calcium and other minerals to initiate the bone tissue. These images indicate cell proliferation and bone formation on the surface of the samples as time progresses, thus proving the sample's biocompatibility. In summary, the obtained results demonstrate that the examined samples the isotropy of the examined samples, and their potential to be used as bone reconstruction implants due to their corrosive resistance and biocompatibility. Thank you very much for your attention. The next speaker is my colleague, Itamar Tulpan.
Thank you very much, everyone. The next project that we want to introduce concerns the development of novel print-cast interpenetrating phase composites, or IPCs. An interpenetrating phase composite is a type of composite material where both of the constituent materials are continuous and they intertwine with each other. In our research, we developed a very simple two-step process in order to develop these IPCs. First, we 3D printed lattice materials, lattice structures out of a titanium 6-4 alloy. And then we infiltrated these lattice structure, the pores of the lattice structure, using cast aluminum alloy in a high-temperature environment. The resulting IPCs combine the properties of both constituent materials as well as of the lattice structure. Here we can see the actual lattice structures that we printed, and we can see the resulting IPCs after the filling process. In this type of process, there are two main challenges that we overcame. The first challenge is the very act of filling up the pores of the lattice structure, since the aluminum alloy does not flow very well inside the inside of the lattice structure. And the second challenge concerns the bond between the aluminum matrix and the titanium lattice structure. Here we can see sections of the IPCs that we produce, and we can see scanning electron microscope images of the titanium lattice on one hand and of the aluminum matrix on the other hand. And we can see that an interface layer had formed in between the two materials, which allows the aluminum to bond to the titanium lattice. We investigated the phases that make up this interface zone using electron diffraction, and we identified a variety of different intermetallic phases that formed during the cooling process. Interestingly, we see that there was an extra phase that formed in the BCC lattice in the upper area. These polygonal phases that formed they form in the aluminum cast alloy whenever it cools down at a slow cooling rate. And we can understand that since they formed in the BCC lattice but not in the simple cubic, that the choice of lattice structure affects the formation of these phases. We can understand that since the BCC lattice structure has a larger surface area than the simple cubic, it prevents the extraction of heat from the area that's in the vicinity of the interface area, since the lattice structure is made out of titanium and it conducts heat very poorly. And this allows for the formation of this extra phase. We analyzed the mechanical properties of our IPCs, and here we can see the result of compression strain stress testing of both of the IPCs that we produced. We can see a comparison to a rule of mixture prediction, which is a prediction that's based on the ratio between the titanium and the aluminum between for the mechanical properties. We can see that both of our IPCs overperform the predicted mechanical properties. We can see here also a comparison between a variety of different material families in the engineering world. And we can see that the IPCs that we produce have a very high strength-to-weight ratio. We can even see that they have a similar strength to titanium alloys, even though they are, for the most part, made out of aluminum. Finally, we continue our research into producing a variety of different IPCs. Here we used polyether imide, or Ultem 1010, as the matrix material, which is reinforced by titanium 6-4 lattice on one hand, and a lattice structure that was 3D printed out of polyether ether ketone on the other hand. And we can see excellent filling of the lattice structures in both of these IPCs. We continue to research this subject, and we hope to publish in the future the results of these studies, as well as a variety of other materials that we are creating. Thank you very much. I am pleased to present the next speaker, my colleague Sahar Halevi.
Hi everyone. Today I will be presenting my research on high-performance polymers for bone replacement implants. In our lab, we primarily work with two high-performance polymers, PEEK and Ultem 1010. These materials are widely used across industries from lightweight aerospace and military parts to surgical jigs and tools. These materials have high mechanical properties and thermal properties, and for that they need specialized equipment to print with them. And to print these polymers, we use a high temperature printer. This printer can reach a printing temperature of 450 degrees Celsius. This printer is also equipped with a convection heating system that works like a heat gun. It reduces the thermal gradient around the printed parts. And this is an open source printer, and most open source printers don't come with preset parameters from the manufacturer, and for that we need to perform a parameter optimization for each material that we use. And for that we conducted an optimization workflow or optimization process that is constructed of 4 stages. In the first stage, we optimize the printing temperature. The second stage, we optimize the DAS or the convection heating temperature with the printing temperature from the first stage, then the heat treatment temperature, and finally, we validate our results by comparing our optimized parts with parts manufactured on an industrial grade printer. Here you can see an example from 2 different stages for each of the polymers. We achieved optimal ultimate compressive stress for a DAS temperature of 440 degrees Celsius for the peak, and an optimal ultimate compressive stress at a heat treatment temperature of 225 degrees Celsius. As we know, in FDM printed parts, there is an anisotropy, and for the comparison stage, we printed 3 different printing orientations, and we tested their compressive stress. And as you can see, the blue graph represents our optimized parts. The red one represents parts manufactured on an industrial printer, which is the Stratasys Fortus 450 MC. And as you can see, our optimized parts present comparable results for when comparing to parts manufactured on an industrial printer. And as I mentioned earlier, these materials are designated to be used for implants, and this is an example of from one of the biocompatibility tests we are performing. This is an in vitro indirect cytotoxicity assessment, and as you can see, the cell viability for both materials is well above 70%, and this, in fact, according to this standard, shows us that these materials are non-toxic, and it shows us promising results that these materials can be used for future implants. I'm proud to present the next speaker is my colleague Noah Gabay-Bas.
Hi everyone. I will present my work on the development of a bioink for bioprinting of patient-specific skin patches. Okay. So what is bioprinting? Bioprinting is defined as the use of 3D printing technology along with materials incorporating living cells for tissue regeneration, for regenerative medicine. We combine materials, particles, matrix, and cells to create a bioink. So we actually, in our research, use 4-dimensional bioprinting when the 4th dimension is time. And over time, the printed models is inserted into an incubator, and after a few weeks, we achieve an initial tissue. So our goal is to create this kind of bioink that is patient-specific. What does that mean? We do that by material selection. So we use polymers, cells, and proteins that we take from the human body, and we aim to take it from a patient once they need it. and combine them to create HealInk, which is a human-derived engineered autologous live ink for tissue generation. Once we determine the composition and the printing parameters are established, we print the model and put it in an incubator for a few weeks. After incubation, we achieve a skin patch that is a developed tissue, an initial tissue, that is 100% matched to the patient. So the first thing we did is to determine the composition of the bioink. So we tested several compositions of the HealInk bioink. The first test we did is a relaxation test, and we see that all of the compositions behaved quite similarly with a rapid relaxation rate that is beneficial for cell growth. The next test that we did is to determine the elastic modulus of the different compositions. And around 20% we see an increase in the elastic modulus, meaning this hydrogel is stiffer and more stable. And therefore we chose that as our ideal composition. So for the printing process, we use Cellink Bio X6 bioprinter. It has several printheads and functions that I'll show you in a minute to deposit the materials in a controlled manner. The first function that we use is for the bioink scaffold, and we use extrusion-based bioprinting. We push our bioink through the nozzle using pneumatic pressure. And the other function that we use is syringe pump bioprinting that we use to seed the cells onto the bioink scaffold. So now I'm going to show you images, microscopic images of our cells after incubation. So this is an image of human dermis cells after 7 days of incubation. In blue, we see the cell nuclei, and in green, the cell cytoskeleton. First of all, after 7 days, we see that the cells are alive and well, meaning our bioink is not toxic, as we can assume. And now, after 21 days, we see the cells have multiplied significantly, and they create this kind of continuous tissue. So we see great promise for this bioink for skin bioprinting, and also in the future for further tissue applications. So thank you very much for listening. I see that we have a few minutes for questions for either me or my colleagues. Thank you.
Incredible work. 2 minutes to spare. Yeah, we have just a couple of minutes for questions. So if you want to ask a question generally, and then whomever is best suited to pick it up can pick it up. Or where else can we find out more about the research and monitor the research? Troll the.
There is a website.
Okay.
And also my email.
Yes, you can contact us and we're still here, so you can approach us later if you want.
This looks slightly different than I was expecting the laboratory to look like.
Yeah, this is the.
Okay.
This is a group thing that we did. Yeah, fun day. Yeah.
Okay, I like it. Thank you very much. Excellent. Thank you.